Yeah, hello everyone. Thank you for joining us today for another exciting webinar. Today we'll be talking about virtual screening, and before we begin, I would like to just remind you the rules for the webinar. So you will be muted during all the webinar, and if you have any questions you would like to ask to our today's speaker or myself, please type them in a Q&A window here down. You can find it down. Then if you have any other questions, remaining questions, feel free to connect with us via email, via social networks, and basically ask them. Also, you will be given the link to the webinar, since it will be recorded, and it will be hosted on YouTube, our YouTube channel, so you can then share it with the colleagues who were not able to join. Yeah, so that's all, and obviously please follow us on the social networks like LinkedIn for other upcoming exciting webinars. So with that, I would like you to introduce to you our today's speaker, Dr. Günther Stahl from Cadence Molecular Sciences. And Günther received his, graduated from University of Bonn, then he received his PhD from University of Düsseldorf. And after he joined, he was pretty extensive. He has pretty extensive industrial experience. He worked at Tripos, at Acceleris, and now he works for more than 13 years at OpenEye, and now it's Cadence Molecular Sciences. So yeah, so Günther will, as I mentioned earlier, explain how Cadence Molecular Sciences, OpenEye, will help you with your virtual screening initiatives. And before we begin, obviously, we would like to mention a little bit about our product, which is actually been used for a while and extensively in such initiatives, as again Günther will be talking about. That's enamine real compounds. So I'm gonna share my screen and just remind you a little bit what we have there and how we created the collection and how we can how that can be used to address your needs. I hope you can see my screen now. And it's changing. So enamine real compounds. Real is an acronym for readily accessible, and this is our approach to address a synthesizability issue when we try to predict what molecules are synthesizable and what are not synthesizable. And for us, it's a way to basically assess these molecules using synthetic procedures that are validated at enamine, and these procedures are applied to enamine in stock building blocks. This approach is not something that we actually came up recently. We've been synthesizing compounds since 1991, and by the way, next year will be our anniversary, and we're planning some events. So please follow us on the networks. Yeah, we've been synthesizing compounds since almost 35 years now, and with that, we've collected a tremendous experimental experience in compound synthesis. And this experience allowed us to generate more compounds. We call them make-on-demand compounds out of, based on the information that we received from the synthesis, from the actual experimental synthesis. And the way we use this information, we can analyze which building blocks can be employed in that or another reaction, and basically take into account this for building virtual spaces, as well as use the information on the synthetic procedure overall. The growth of Enamine Real obviously is supported by our in-stock compound collection of building blocks. And as you can see, it's actually growing every year. So we have at least 20,000 new building blocks delivered annually. Yeah, that's pretty much how it is. It's you know, our collection of building blocks, it's a basis of Enamine Real and its expansion. For the Enamine Real compounds, which I just put approximate number to zillions, we have a few subsets available, which include the real space and the real database. Those are most utilized subsets of enamine compounds. And obviously these subsets of enamine real compounds, they've already been projected on our screening collection, and the number of liquid stock compounds and preplated libraries. And as I said, Enamine Real has been popular for quite some time now, and there are numbers of publications appeared in the literature citing our product. As I said, we constantly developing and expanding our collection of make-on-demand compounds, and Enamine Real is one of them. So we always try to be proactive and add novel synthetic procedures and obviously newly developed and synthesized reagents into the enumeration, so we can have the space, Enamine Real space, for example, and Enamine Real database and other products expanded. So, and as you can see, the growth is constant for this type of products. And these are few ways to access our real compounds. We have Enamine Real Explorer tool that allows to search for all the compounds in one place that's developed by Enamine. The compounds can be downloaded as enumerated sets, or they can be accessed through syntons and the rules to combine them. They can be accessed through our partners from ChemSpace, and you can find Enamine Real compounds through numerous services and software tools, databases like Zinc, like Hyperspace, and others. So yeah, that's basically a short intro to Enamine Real, and I would like to hand the stage to Günther, where he explains how they actually address virtual screening projects. Yeah, Günther, I'm gonna stop sharing, and yeah, the stage is yours.
Thank you very much, Yuri. It's always amazing, and I'm always amazed to see how big you guys got by now and how much you can do with your libraries and the effectiveness of what you do. So every time I see this, I'm just, wow. Anyways, my name is Günther Stahl, and I'm application scientist at OpenEye, as Yuri mentioned. Sharing my screen to start with, I wanted to let you guys know about, I want to start here. OpenEye, in case you don't know us, we are in the field for 25 plus years now, servicing the computational chemistry, and molecular discovery units of our customer base. And about 3 years ago, we were acquired by Cadence. Cadence, if you heard of them, they are a global player in services, software services to chip manufacturers. So the design and the solution, the layout of computer chips is what their software is. They have a few adjacent businesses now as well, computational fluid dynamics, simulations of whole data centers. So they are a solution provider to all the big chip makers. So a good chance any kind of your computer chips in your laptops, in your phones, in your cars, in your dishwasher, they might have during their design period seen some kind of Cadence software. So really a global player with a lot of experience in solutions, in algorithms, in solvers, And they were interested to go into the pharma biotech area with us as the core, combining their expertise in solution with our expertise in the physics-based modeling. And we're really excited to see where together we can go and how far we can push the envelope here. Anyways, today's webinar is really about Enamine and how we utilize the Enamine real libraries inside our tools. We have multiple places where this actually lives. And one of the major places for us is the platform that we started to create about 10 years ago, thinking about how we can put our applications together under one roof, under one umbrella, which could be either a local downloadable software piece for your PC, or at that point, we decided to make this a cloud-based platform. So from the ground up, combining the ability to create and edit the applications that we have and putting them together with third-party tools, because we didn't write all the code in the world. So we combining methods together to solve problems. That enables us to calculate really complex solutions and putting them together on small and large scale, especially utilizing the scalability, the power, the resources available on the cloud in an automated fashion to really do what's needed to solve the problem. To analyze the data in the cloud, so you don't have to download, upload, send files around, and then collaborate with my analysis with my teammates to say, okay, this is what I think, what do you think? And we can start discussing about the projects by logging into a browser, and everybody can just work from their own machine. I could talk more about the platform itself, but I thought it's probably better to just show you how it looks like. And this is my login screen to go. Here's a number of projects that I started or that my colleagues can start and invite me to, so we can work together on something. And for this webinar, I thought I'll just look at the PDB on kind of what's new there. So I found one of the latest releases, one of the late structures that was published there, a PARP1 inhibitor structure. And I thought, okay, that might be an interesting starting point for me, see how it looks like. So I downloaded the PDB file. I prepped the PDB file with our protein prep tool to add the hydrogens and add side chains, all that is needed to make the molecule ready to go for me to work with. And I also prepped a reference structure to say, okay, how does it compare to a known compound that I know about? So the reference structure and my structure, turning them on, putting them into 3D. In my 3D window here, I can zoom in, I can rotate this around to take a look at the active site. For now, I don't need the scatter plot in the spreadsheet, so let's just focus on the 3D page, make this a bit bigger. And if I want to take a look at the active site, there's a quick button here that creates me the surface over the active site, so I can really see the groove and the pocket that this ligand sits in, making interactions here on the left and on the right. So now I compare this known crystal structure to the prepped crystal structure that was published recently. Actually, I should, maybe to make it easier, color my ligand in a different color. So the co-crystallized one I knew about is in this petrol color now. And comparing these two, I can see that, well, they are identical on the left-hand side. They did a variation on the right-hand side for this molecule. Fair. Could still be interesting to see, is this molecule available to me? Do I have this in my in-house corporate library? Can I get this from Enamine? So a quick way to go there now is to do on the ligand a right click and say send to molecule search. This is one of the places where the Enamine libraries live for us that we have prepped. So here the molecule, and the fastest way would be a 2D similarity search. If they are identical, I would get a 1.0 for the similarity value out. And let's use something that is maybe corporate size library or approaching it. Here's a 2 million size library. That's the US liquid stock from Enamine. So if I use this one to start my search, let me see if I can get this one smaller. To do my search, that's about a second or so to do the search in these 2 million molecules. And I can see 2D similarity, none of them is 1.0, so it's not identical molecule, but there's very similar molecules, and they all seem to actually share this bottom half, which was the left-hand side that is similar between both of my molecules. That seems to be at least a core that is available from Enamine, or in-house, in this case from Enamine. You can purchase those. So that's interesting to know, not identical, but maybe if I go a little bit bigger and search a little bit larger space. So the largest one we have here for quick searching is about 1 billion molecule, 900 million. That's the samples from Enamine. Samples library. That search also is about 2 seconds-ish to get back with results to me. And I can see that still no 1.0, but yes, all the molecules, they do carry very similarly that bottom part of my fragment. So, okay, if now I'm interested in these molecules, let's go back and say, I really want to find everything that Enamine has to offer to me with that fragment. So then we're in a substructure search. And I make sure that I only search for the piece I want to do. So this is my substructure I want to find. I search the same 900 million molecules. I hope there's more than 100 hits in there. So I'll increase my number of returned hits. And well, I know there should be 2,685 of those, which actually, yes, there are. And now I have all these molecules that carry my substructure, and I can save them out into a data set to use into my hits directory, save that data set so I can use it for further analysis. And that's what the platform here combines. I can take my molecules now from my data set. These are all 2D hits. So they are 2D structures. They don't have a 3D. And these 2D structures, here's my 2,685 molecules. A quick way would be to use this rocket to take the next step. And here's my recent workflows that I executed. So I did prep a protein. I did some comparison with small molecules. That's something we're going to use later. I could filter a hit list. These are different tasks that we have prepped for you. And one of them is docking with a 2D small molecule input. So I start this, what we call flow. These are our task-based solutions. I write the results to also my hits directory. And my 2,685 molecules are pre-filled as the ligand database. The receptor I want to dock into is the one that I prepped earlier, my reference structure. So that is ready to, that one is ready to go. Apologies, somebody seems to be calling me here. I need to take that one off. That is, I thought I put a do not disturb in here. Obviously, I did not. So let me get back to my presentation and share my screen again. So I pick my reference structure and use that as a data set. The rest here is pre-filled, so I can just check. I have nothing else I need to do, so I can easily now go and start my job. It goes off, does my calculation for me, and the docking is going. So this is a way to do 2D. Now, molecules are not only 2D, molecules are 3D. So let's go back into our analysis here and send this molecule again into our molecule search. And you might have noticed before or not that there's a little 3D window down here. The molecule that came in from the crystal structure has 3D coordinates, and we can do a 3D similarity search here as well. The libraries we can search here, again, many of the Enamine choices and a few others, that's what we prepared. And here's the largest one we can do in this interactive way of 235 million, another sample set from Enamine, 235 million molecules. Let's look for the top 100 molecules from here and start that job. So while this is going, let's talk about 3D a little bit more and how we represent molecules in 3D, because ultimately for interactions with a protein, this is not a molecule, it's a 2D graph of a molecule. Now, if we put it into 3 dimensions and create a conformation of this molecule, first of all, it's one conformation, so we need to deal with multiple conformations. The molecules are flexible, and we do that. So still, this is not the molecule that the protein will interact with, not the entity that the protein actually sees. So what we do in the end is we create the shape, the volume of that molecule, and that's the 3D object that we use to compare and we use to calculate. And we decorate this 3D shape with either electrostatics, so positive, negative charges, van der Waals interaction surfaces, to make use of the interactions that the protein can see and work with, or as an abstraction, that's what you see here, and that's what we do in our rocks tool, is we use chemical features to represent those. So the three dots you can see here, the three green dots, are representing obviously the rings of the molecule, with a fourth and a fifth down here. We have acceptors, donors, cations, anions, to represent the features that the molecule exhibits to the protein and can interact with the protein. Now, those look like spheres computationally for us. In the tool, they are not. For visualization, we put spheres in. They are atom-based three-dimensional Gaussians that actually, as a Gauss function, kind of stretch out into infinity, which really helps by comparing two molecules. If features don't overlap right away, they still feel each other, and we can use this to pull the features on top of each other to make sure that we have as good overlay as possible. So we're very smooth optimization surface through this, and no breaks in between. That's really helpful for storing and for comparing and calculating similarities. So a molecule for us is a shape and the chemical features, and if we have two molecules we compare with a rather dissimilar graph in 2D, not sure if you see the similarities between those right away, but if you find the correct conformation and you look at the shapes of the molecules, it gets clearer that, well, actually, they might occupy the same space in an active site, and they might make the same interactions with the protein. If we use the shapes to align them, then take the shape away and look at the atomistic overlay on the right-hand side. Yeah, those might fit into the same active site. They actually do. They are active against the same target at a similar activity level. So our shape way of describing molecules is really good representing biological similarity then as well, which is harder to do in 2D. We are not depending on the atomistic composition, but we can still pick out interactions and activities between two molecules. So if we look at this now, how this works in the interface, here are the results. It takes about a minute for the 230 million molecule comparison. Here is our initial structure. And here is an overlay that we find for these molecules. And we can see, yes, the shape representation is really good. They fill the same pocket. They don't make exactly the same interactions down here. So there is no carbonyl group on my molecule, but an acceptor. So that might be good enough. It's not an aromatic, but an aliphatic ring on the side. Kind of why not? So these are alternatives, possibilities that might be useful. And this one is the most active one, or the highest scored one on our Tanimoto comparison scale here for shape and color. The scale here goes from the sum of a shape Tanimoto plus a color Tanimoto of up to 2. So 1.3 is the highest we can find in this set. If we look for something that has a high 2D similarity, like this guy, then we are back to, yes, we find the molecule with the same framework that we had before. So kind of best of both worlds. We get molecules with very high 2D similarity, but also things with high 3D similarity. This is low in 2D, so they might be novel, they might be different, and could be an alternative and a way to get away from a known scaffold to something different, still active, hopefully, for you to buy from Enamine, test it to see if those work. And then you can pick those molecules, take all 100 of these molecules that we have here, and do more work, docking, whatever you might want to do. So these molecules here, I told you, are kind of limited in size for the interactivity that we have. This runs on a graphics card, this comparison in 3D, and that graphics machine has a limited amount of memory. So the maximum we can put on there right now for an interactive work within 1 minute is 250 million-ish molecules. Obviously, Enamine real database, it's much bigger. And to search the bigger one that we have prepped, so you can use it, we actually have to use something that you saw before, and this is a flow. So here is a library of the things, the tasks that we can do. And if we search for fast rocks, there is a fast rocks plus flow that allows us to use a molecule as a query. And here we will use our co-crystallized ligand as the molecule to use. in this flow, we can actually do what we did before in 2 steps, like saving out the file with the hits, then running the docking on those best molecules, on those molecules. Now I can use the best molecules from the ligand similarity and right away choose a design unit to dock into and dock the molecule. So that's the way of combining things together. And now I need my input collection that I want to search. And my input collection lives in the organization data because that's shared across projects. Could be your data sets, but here now we use the one that we prepared, and here's a FastRox collection. And here are the collections that are ready to go. The enamine liquid stock, 3.5 million molecules, the 230 million molecules we saw before, and the 23.5 billion molecules, which the enamine real space enumerates to when you do stereo enumeration on the molecules. So I use this collection as input. As before, more options, you don't have to do anything. Good defaults are here, you just start the job. So now this goes out and starts running everything in the background for me. I don't have to deal with AWS, I don't have to be an expert. Here's the docking run that was going here. This FastRox Plus run started to go now as well. So you might be wondering, how do I get my databases in there? So the database prep that we do and that you could do for your libraries as well. For that, there is, as you might have suspected, a flow that we use to do this. And here we prepare Giga collections. Any kind of input that you have, SD file, OEB file, SMILES, so any kind of molecular file we can probably read these days. You would launch that flow, you enter your files that you uploaded before, your molecular library, and then there's options to do filtering on the fly of molecular weight ranges, log p values, unwanted substructures, stereo enumeration, yes or no. So options that you can do, again, those are all good defaults, and you can just run this to do. The libraries that you saw that we pre-built for you at the moment is enamine libraries here, the enamine real database of the 23.5 billion, enamine real samples, an HTS set of the 3.2 million, some other vendors with smaller libraries that we prepared, plus obviously your libraries you can put in and prepare yourself. Now this is a one-time cost you have to pay for, and for your own libraries. These we cover because these is a service of us to you as our users. And to give you an idea of how expensive this is, 20 million molecules, 27 million, that's about $100 to AWS because we rent their CPUs, we rent their GPUs, so they want to get paid for this. The really a big cost factor is once you go billions of molecules, this is a real cost, and we'll take this cost as a service to you right now. So you don't have to pay this, and not every company has to pay this for themselves. So this is a service we do, and we do this whenever Enamine comes up with a new version of the Enamine real database. We'll do this exercise again and publish, hopefully within a few weeks after the library drops from Enamine, the latest version on Orion, to be able to help you out. And you can search the latest that is available there. So going back to my search, just to give you also an idea and looking at what's going on in this FastRox Plus flow, here are all the individual pieces and tasks that are performed along the way. So in orange is active cubes that are doing something, active tasks, pieces of work done. And so this is a flow-based pipelining environment that can be rearranged and be put together in this way. We are using 50 CPUs right now in the back. There's 2 GPUs already running, and the GPUs do, if we zoom in on the FastRox cube, the GPUs do the actual comparison work here. So 2 instances are running. 2 won't be enough to do this in a reasonable amount of time. So this will keep growing over time to more and more GPUs. How big does this have to go to actually finish at some point? Well, let's take a look, because I took the metrics of that cube when I ran this before. And for the first 10, 15 minutes of the flow, we're asking for more and more GPUs. So in the end, we get more and more GPUs from AWS, up to 1,000 of them. So 1,000 GPUs will work in parallel for me to solve this problem. And that takes about here, what is it, 20, 25 minutes or so. So altogether, half an hour, 40 minutes to get the 223 billion molecules compared. That's 235 billion overlays because we have 10 conformers per molecule. Flexibility needs to be taken into account. So 235 billion molecule comparisons in about 40 minutes. The flow together runs a little bit longer because after that we do the docking part of the best molecules. So the flow runs a little bit longer in the end and does cost in this environment altogether about $300 to do searching plus docking and get me the results. How do the results look like in the end? Well, for that we can go to data again, and in my data section in the FastRox plus results directory, there is a bunch of solutions with the top 10,000 hits from the ligand-based comparison, the top 10,000 after the docking. Those might be different molecules. And in order to not click too much, I have this prepared in my discussion board that I would share with my colleagues. For my data, there's an analysis discussion board where I started to post the first analysis of 10,000 molecules running against 23 billion, filtered by best docking score. This is a link. Clicking this link brings me to my analysis view that I left with here. So I can show this to my colleague. They can go over this themselves. And they have together the 3D view of my active site, a scatter plot, and the spreadsheet. Make this a little bit bigger. So here's my initial structure again that you saw at the beginning. And now I can take a look at the best docked molecule. This is the docking score. Negative is good. So the best docking score, and this is the pose of the molecule in the active site. How does that look like? Is that something that is interesting? It does have the same fragment here in the bottom, making same interactions. It has an additional acceptor here that might or might not be interesting. So this is one molecule. I can just use my arrow keys, go down and see other solutions going down my hit list. Similarity. Now this structure is at least going where the co-crystallized ligand was, so that could be something interesting. And I do remember seeing, because this is the 2D similarity in color here, the first molecule with a high 2D similarity is one now with the substructure that we had before. So we do dock those molecules in the same way and maybe pick up interesting new interactions along the way that the other compounds did not. So that's a way of looking at this and sending this now. And the next step could be running a short MD simulation on this docking post to see if this actually holds together, even if we let it loose for a little bit. So all this is further steps that we can do all in this platform to do more and more analysis. So before I wrap up, maybe one more goodie on what you can do with shape and shape-based comparisons. This is work that Relay Therapeutics released not too long ago. They were working in the COVID era on the structures, the fragment hits that were created by the diamond light source. So there is a bunch of fragments, screens, and crystal structures that you can find where the fragments sit in the same active site, sometimes close to each other. So they picked those fragments that are close to each other and converted them into a query, into a shape query. Disconnected features on their own, but asking rocks to find a molecule that fills this shape ideally. So they actually searched enamine, 2.5 million molecules from enamine, and they found a molecule, multiple, but this molecule really fills that shape nicely and basically connects these two fragments in an easy way. Got the molecule from enamine. Turned out this one is a few hundred micromolar hit. With some metchem optimization, regular metchem work, they were able to bring this down to a low single-digit micromolar starting point for a project where they could eventually start exploring the pockets more. So a very quick way to, here starting from fragments, to find interesting new chemical matter. The summary for me now is that this Orion platform offers all kinds of tools. For today, I focused on the hit identification piece with the large-scale databases, structure-based screening, ligand-based screening. There is ways to analyze the protein to begin with, finding cryptic pockets with an enhanced MD method to see what opens during an MD and are there interesting pockets that come in and out. SiteHopper to compare the shape of active sites to see, in the same way we do ligand shapes, now we do pocket shapes to see if my ligand binding into this pocket, if I compare the pocket shapes to other proteins, maybe my ligand binds somewhere else as well, because it's the same shape of the pocket. So that's maybe off-target effects, or find other active matter, chemical matter in other proteins which bind here, so they might bind my protein. Different ways of approaching this hit identification afterwards, and lead optimization to do bioisosteric replacements, find new cores, find new side chains, get around tox problems eventually. Short trajectory MD is what I told before, when you just let it wiggle for a little bit to see how stable interactions are, all the way to relative binding free energy calculations to really predict the activity of two molecules that are rather similar from the same series in lead optimization. All that is realized on the platform, and all that is something that you can just use out of the box because we create these flows. But you can add your own tools into this as well. It is an open platform to use and go about. So with that, I think I will stop talking for now so we can get to some Q&A. Thank you very much for now.
Thank you, Günther. It was really nice presentation and nice demo. So yeah, so we already have a few questions. I'm gonna start with them, and yeah, please, if you have other questions, please type them, as I mentioned, this Q&A box. Yeah, the first question is, how can I access the molecule search tool you showed in the presentation?
Okay, the molecule search tool is available on this Orion platform as a total thing, so it just comes as part of Orion when you log in. There is a way to just access the molecule search without all the other computation chemistry stuff. So that would be for maybe med chemists who only want to do the searching, the enamine comparisons, and finding things in libraries. That's a way to a cheaper entry a cheaper entry point maybe into the searching part, into the Orion world, so you don't get all the other flows, but you can go. So both of those are available, the full package or the quote unquote reduced to just molecule search and the prepped libraries.
Yeah, thank you. Can I modify the search query for rocks, adding important target information?
Oh, I guess when you know your own, when you have some information of what's important. So yes, you can on the features that we have add weights to say this donor is more important than the other donors in my molecule. You can delete features from these queries and use that as a search query. So yes, you can put your own knowledge, you can put your own bias into the query to say, I know this is important, and run with it. So yes, you totally can modify and customize your queries.
Thanks. Other question is, how expensive are searches with molecule search? Well,
so I told you the price of the full enamine 23 billion. I think that in the end was kind of $300. The molecule search itself is free. The machines are sitting 24/7 ready to search. So the machines are kind of paid for in molecule search, and searches there don't cost anything. You can go over and over and running those, as those are machines that are standing up and cost nothing on the defaults, because that's again a service that we do. If you set up your own databases and upload your own molecules and your own databases, in-house libraries, that's an additional server to start up and have running. So that's cost that we will put back to you, because that's nothing that we host. But the ones we host are basically free on the molecule search side.
Thank you. Another question, is there a way to incorporate MD simulation to sample conformers and then do 3D similarity search?
So the conformer ensembles that we search, we create with a fast way that we created years ago called Omega. So that creates the conformer examples. You can run MD and take snapshots from the MD for the conformational sampling. We don't recommend it as much because you might be limiting yourself and you never quite know if it's enough. So the searches that we do with Omega are pretty good covering, but yeah, if you have a different set of conformers you want to search, obviously, yes, you can upload them, prep them, and have them ready to go and search. That's really up to you if you want to do this yourself. On the platform itself, there is no easy flow, as we have a different solution with Omega. There is no easy flow to do this in an automated fashion, run and then analyze and pick conformations from the MD simulation itself. That could be set up. We haven't done it because we have the Omega solution to create our ensembles.
Yeah, thanks. Yeah, can you please comment on the algorithms behind the scenes used to run docking and MD experiments?
The algorithms behind the scenes to run docking. So we use a conformer ensemble of ligands. We use every conformer one at a time to exhaustively place them in the active site everywhere. And then we filter down, obviously, those positions that have clashes and optimize those that fit into the active site rigidly. Therefore, we have multiple conformations of the molecule and realize every conformation of the molecule. We optimize them rigidly to the best interactions they can make in this specific conformation. That algorithm is very fast because there's no optimization on the fly involved. And B, seems to be performing as well as any other docking tool out there. That's our docking tool that we used. We have a collaboration with CCDC, for example. So Gold is available as an alternative docking tool on the platform already. If you have your own docking tool you want to put on there, that's totally possible as well. Once you get to a managed service and you have operational freedom to put in whatever code you want. So our solution is a rigid docking solution that takes into account multiple conformations for the molecule to find the best fitting conformation. I hope that answers the question.
Another question. Can you please comment on your diversity subsets of enamine real space? So basically, I believe that's related to those 23 billion molecules and that smaller set. Can you
So the
comment on
23 billion molecules is actually the enamine real space of 10 billion stereo enumerated, because now we need to decide R, S, or both, obviously, if there are. So that stereo enumeration brings the 10 billion to 23 billion. So we didn't do any more filtering there. The other subsets is also really just what we get from you guys. So what you call the samples, I'm not sure how you pick them actually, is what we use and just take them as they come.
Yeah, thanks. Well, yeah, I can comment on this, just, how we actually sample the space, basically evenly taking every other molecule to make the, the subset of the corresponding size. Before we've done, the diversity picking, but in fact, it's hard to perform such an exercise on a tens of billions of data sets. We don't have enough memory or, machine. So the simple sampling, if you wish, it works pretty well here. Okay. Another question is fast-rock physics-based method of molecules overlay generalization or includes ML? And what's complexity measure scalability for fast rocks, I believe?
So there is no ML involved in this one. This is a physics-based method comparing every conformer of the molecule in the database to the query conformation that we are searching. By the way, the query conformation doesn't have to be a bioactive conformation. It can be even a low energy conformer of a molecule. So even without crystal structure data, you can use the ROX comparisons, as it just depends on a good starting conformation for the query molecule. The second part of the question was about...
What's the complexity measures? I believe scalability. That's how scalable it is, the method.
If I get this correct, it's stupid parallel. We just look at every molecule. So we split our data set into multiple chunks and send this to its own GPU for fast rocks or CPU for the docking task and the rocks task. And we just need more CPUs and GPUs. And that's why in the background, the scheduler just acquires more and more GPUs to do this in an hour to get the job done. If we only scale to 500 GPUs, well, it takes 2 hours to do. So it's a quote unquote stupid parallel task to split the database and send them to over. So the scalability limit of 1,000 GPUs here was artificially set by us to not overwhelm or not ask and capture everything that's out there, but it's an artificial number that we put up to say 1,000 GPUs. Now with libraries the size of Enamine right now, we might want to increase that number, because then we get it done in 10 minutes if we scale it to 2,000 GPUs. So that's just a trade-off between speed and a number of things administration-wise we can do. The cost will be the same. 2,000 GPUs for 15 minutes versus 1,000 for half an hour. It's the same price. So really, it's just a matter of how fast you want it done.
Thanks. Is there a mechanism for graduate students to use these tools for no cost, like an educational package?
There is an educational program we have for the downloadable applications, the toolkits, the programming toolkits that we provide. Orion itself is, we are not able to make this available for free. It's based on AWS. We have to pay AWS resources, so we need the money to actually fund this. And somebody has to pay for this. So that is not easily available for academics right now. The individual tool, the FastRox tool, for example, to do it on a local GPU is totally available, and that is an academic contract. If you go to our website, eyesopen.com/academics, you should be able to find the application form to get free access to our regular tools.
Thanks. How to confirm whether a particular ligand conformer is having better energy, the best energy, I believe. How to find the best conformer.
Now we're getting conformers. So what we try to do in Omega is to create conformers that are similar to bioactive conformations of molecules, because that's what we want to find. For that, we don't use a necessarily minimum energy conformation, because bound molecules are almost never in a minimum conformation. So the global energy minimum of a conformation is, for this task, kind of irrelevant. So the torsion angles that we choose by Omega and running them is designed to replicate bioactive conformations. There is an energy evaluation you can do. There's force fields involved, so you can run force fields. You can minimize everything for some task when we try to find the entropic minimum as well. So including entropy in our searches, we actually do create a large ensemble, minimize everything to the local minimum. So we can do all that. For the task of virtual screening, we on purpose do not go for minimum structures, because bound conformations are almost never minimum structures. So the energy is an interesting discussion, but only a side discussion for this task, to be honest.
Thanks. Well, there is a question about comparing Orion and your tools to other, similar 3D search tools like Aliferon's Pharos, Cresset's Ignite, and obviously Infinicy from BioSolidity. Have you actually compared, the tools?
They never gave us access to their tools. Neither did we to do a head-to-head comparison. So customers can do that. I know ROX and FastRox are used widely over the years, so people trust the way we do this. We do have information, and we do have a paper that I'm happy to share, that Abbott back in the day created a belief score to say, and really showed on their internal targets, that a similarity calculated with ROX really is representing the biological similarity or the biological activity between two molecules, and the probability that two molecules that are high in our 3D Tanimoto combo similarity are active against the same target. So that's interesting proof that this method actually works. In terms of performance and selection to the other tools, I can't really comment, because I never used them. I know that ours seems to be working fine, and that's why we try to make it as easy as possible for customers to run them and use them. So yeah, sorry, can't really answer on the competitors' tools. Don't have them.
Thanks. So you mentioned this Enamine liquid stock collection a few times. So what it is? Yeah, maybe I can comment here. Yeah, so that's a new collection that we've established at our facility in New Jersey, in the U.S., and it sits in Hamilton's robotic storage. So the compounds there, and yeah, you mentioned over 2 million molecules. Now we actually a little more. Now we have 2.3 molecules sitting in the solutions in that robotic storage, and these compounds can be really formatted and delivered to your location, especially if we're talking about within the US, really fast, within 1-3 days. So this is something that that's again really new for Enamine. We'll be having a few posts about it in the upcoming weeks. So yeah, again, please follow us and yeah, inquire for the file from the account manager, because this is really a good collection of compounds that can be accessed fast, and molecular docking is one of the applications that can be used yeah, for this, as Günther just mentioned during the presentation. Okay, so there's
Yeah,
a few more
docking really
questions.
is for a few million compounds. That's really not a big deal here on, for example, this platform. Even the whole Enamine real database of 23 billion, we could brute force dock. There is another solution with ML included to learn the scores and not dock everything. That is available, so that makes the whole run quite a bit cheaper. So at 1/10 of the price, we get most of the hits that we would get from a brute force docking. So multiple ways of dealing also with larger ones, but the 3 million molecules is yeah. We do this for lunch.
Yeah. Another question: do you have or work now on de novo design as alternative to screening? E.g., use an intelligent search algorithm to explore the chemical space covered by the combination of reagents. So have you done this before? Yeah.
So the de novo design, so combining reaction-based combining of building blocks fragments to enumerate eventually trillion-size libraries is something we're actively working on. That is something that's probably going to be released beginning of next year. So wait a little bit. So there is a solution coming from us as well to do these trillion molecule size and only enumerate the part that you're interested in once you do your similarity searching. So that is certainly something coming. There are other ways of generative design in other tools. So our isosteric replacement tool here, there is flows where you can just tell the enumeration to pick any fragment in there and replace it with something else. So then you can just enumerate a large new library of yet unknown molecules that might not be easy to synthesize because there is no synthesis rules involved in that bioisosteric replacement way. But then you can go back to do similarity searching. If this is a really interesting new scaffold that is not identical available, but maybe something similar, so you go back to molecule search, run comparisons, screen the Enamine library for something that's similar enough on these new ideas. So there are ways, but the trillion molecule synthon-based searching is something that's coming soon.
Yeah, looking forward.
First official announcements will be in a few weeks. If anybody wants to come to our mini cups that we hold in Japan or in the US, please do, because there might be something at these mini cups.
I totally agree with you, Günther. So when we use fragments, they have one conformation, but when we combine them into whole molecules, the conformation might be entirely different. So how to address this issue?
The shapes that we're trying to fill, I guess it's referring to the shape fragment example that I showed. The volumes that we try to fill, we will fill with a conformation that we have in the database, which is a reasonable conformation for a molecule, at least kind of low energy conformation for the molecule, hoping that in the combination, this is a real conformation possible to fill that space as intended, as the fragments did bind. So yes, the new molecule might be able to adopt multiple different conformations, but at least if one conformation will fit my requirements, we would assume that this molecule will adopt this conformation in the binding site. And in the example from Relay, that seems to work. It is an active conformation that they confirmed actually binds this way. So the shape representation to say, find me something that fits that volume, which is a little bit flexible, a little bit wobbly to begin with, and not nail down the atom coordinates, does work pretty well. So we're not that worried as long as the conformer we find in the database fits the shape.
Thank you. So you mentioned the cost is $300 per screen. Are there any other upfront costs? Also, how do you manage confidentiality of targets when using this tool?
Okay, the security first. So every company, you get your own login for your own company. So we create a space in Orion for you and your company that is firewalled off from anybody else. So that's one piece of your company on our instance of Orion. You can have your completely own Orion version. That's what we call a managed service for your company that only your employees have access to. On each project that you start, you have to invite others into the project to see your data. So that's another level of security. If you just want people involved in your project, you only invite them and only give them access to it. So security is that's the one piece. I think we are, I think, pretty well covered with that, and we haven't seen any problems with this in the past. The other upfront cost. So if you, quote unquote, only want to search our prepped library, the Enamine real database that we did, the 23 billion, which is the number that you saw, that's just provided on the stack. Certainly there's a licensing fee to get access and get membership, quote unquote, on and get an account in Orion. That's obviously an upfront cost to do, like for any other package of software that you want to use. There's a licensing fee, a per user fee that you have to talk to my sales colleagues about, because I try to stay away from the numbers. But that's the initial cost to get access. Once you're there, it's only the cost for the calculation you do. And every calculation, every flow you run has a price point. A few million molecule docking, that's cents. But if you need 1,000 GPUs for half an hour, yeah, those do cost money.
Thank you. How to buy compounds from Enamine after primary virtual hits have been identified?
That goes a little bit to you, but for us, I think that's, you need an ID, the compound ID, and then that list goes to you, and the rest is on you, Yuri?
Yes, that's correct. So basically, you once the compound's identified, you come to us, to account manager you work with, or go to inquiry@enamine.net and basically send us the list of compounds and get a quote from us. Do you have tools to find cryptic site?
We do. There is this cryptic pocket detection tool that really runs an enhanced MD to figure out if during the MD there is a coordinated movement between amino acids that change, one way to analyze, that change the solvent accessible surface together in the same frame of the MD, which means some pocket is opening. Something is happening where coordinated amino acids seem to be opening or closing. So along the MD, we do find these cryptic pockets that are transient and show up and might close again. And the enhanced sampling protocol we do here, based on WestPA, protocol that was created in the University of Pittsburgh in Lillian Chong's lab, is what we kind of productized here. So for people to feed their protein, press the button and see what happens. There is also a co-solvent involved in there to maybe open up pockets a bit more. So it's not just water and salt that we place in there. There's a whole story I can talk about this. And there is actually a webinar from us. If you're interested to hear about this more, go to our website and look for the webinars. There is one on cryptic pockets and also ligandability, because once you find 10 pockets on my protein during the MD run, now which one should I go after? Which one is the one that would actually bind a ligand? So for that, we developed a new ligandability prediction model to say this is a good pocket and this is a non-druggable pocket in the end.
Yeah, thank you. Another question. is besides 2D and 3D similarity and docking, are you planning to implement tools that can enable users to build and run more sophisticated machine learning modeling approaches and obviously explore in real space?
So we do have a whole set of, for us in this building, you saw the FastWorks flow with all the little cubes in there. So these are programming tasks and solutions. So we have cubes for doing machine learning. We have flows that do machine learning based on, for example, fingerprints. I think one thing is, what's the description? What's the vectorization of your molecules? How do you want to compare those to generate those? For some of that we do is actually the similarity of molecules that can be a feature vector. We do part of this already in the docking part, the ML based docking part, where we learn the scores based on featurization of enamine 23 billion molecules. So that is something we already do. If you are on a managed service, you can upload any protocol, any Python, C++ script. You can create your own cubes that do the task that you wanted to, and then reach out to resources like the library in Orion already. Pull that in, do some machine learning with it. So once you're on your managed service, you have full reign of programming basically whatever you want. Then you can use your local script, put it on the platform, use the parallelization and the power of AWS in the background. So then you're free to do whatever you want. So we have some solutions, but together we can probably create whatever people want to do.
Great. Yeah. Yeah, I think there's one last question related to this newly announced liquid stock collection. So what's the concentration there, and what is the purity high enough to enable high concentration assays after visual screening? So the concentration we keep molecules is 10 millimolar, so that's standard concentration, 10 millimolar DMSO stocks, and I believe they're pretty much accessible for all the typical or the most common primary assays to assess the primary hits. As for the purity, we have compounds at over 90% purity based on LCMS measurement. That's kind of the standard for screening compounds we have enamine. Okay. I believe we don't have any more question, and we're a little bit over the time. Anyways, I would like to thank you, Günther, for this really nice presentation and nice, really, and pretty interactive Q&A session. And I would like to thank you everyone who joined us today. And yeah, with that, I would like to conclude today's webinar. And yeah, please follow us on social networks. And if you still have some questions left to Enamine or to OpenEye, please don't hesitate to contact us directly, either by email or find us on LinkedIn. Thank you, everyone.